All right, so today we're going to talk about statistics. Most people freak out about statistics, but the truth is it's pretty easy. We're going to cover a lot of stuff, but let's be really clear. You really don't have to know a lot of math. There are calculators that do all sorts of stuff for you. If you want to know like why something happened as well, there's all sorts of stuff on the internet about Bernoulli, Galton, Fisher, Spearman. There's way more than enough stuff out there. Just trying to figure out what it is that you want to know. Hyperstat is one of my very favorites. This link might have changed over time, but it's an online textbook that'll explain a lot of these concepts. Most of the time, if you know what you're trying to look for and you Google the right terms, you'll find it. One of the other things is that as a student, you have access to LinkedIn Learning. LinkedIn Learning used to be called Lynda. And let's say, for example, you want to learn how to do stats in Excel, or you want to do stats in SPSS. You go inside your portal, click on the top left bar, log in, look at the software tab, link to titles, SPSS, or LinkedIn Learning. Look for that, and then you'll find what you need there. I use it as well to try and figure stuff out. It helps sort through things like on YouTube that you don't know if it's really what you need, or going to a trusted place is way easier. So let's start with central tendency, summary statistics, and we'll cover visuals and correlation. There's so much to do. But really what we're going to talk about is really summarizing data. And go back to how we measure things. Nominal levels of measurement are names that are unrankable. They're just categories. Ordinal level data are like rank ordered categories, like letter grades. A is better than B is better than C is better than D. Interval ratio are two different levels of measurement. Really, they're all, whether or not there's an arbitrary zero or zero is a complete absence, doesn't really matter. Interval ratio data are like your weight, an amount of time, a number of peach trees, whatever those things are. Scale of 1 to 10. Okay, why is this important? Because we're going to talk about summarizing data based on the level of measurement. Nominal data can only be summarized using a mode. Ordinal level data can be used. You can figure out the median. You can also do the mode, but you can't really calculate a mean. But interval ratio data, you can calculate a mean, you can calculate the median, and you can find the mode. Okay, so the whole idea for this next little bit is central tendency. What's the middle of the data and what's its spread? So the one measure of central tendency that you're really familiar with is the average. The average is a single best score that represents a set of scores, and we're used to thinking about it. Just the way that we think, we're like, oh, an average is, and we don't think about what the average actually measures. It measures the mathematical middle of the data. An average is also known as a measure of central tendency. There's all sorts of different ways to describe this distribution. The mean is what we normally think of as an average. Add them all up and divide by the number. That's the mean. But another measure of being in the middle is the median. And the median is the middle number, or the middle score. Another way to measure central tendency, or in other words, where most things are, would be the mode. And the mode is really the most common score. So when we talk about the measure of central tendency, the mean is the average. You really know how to do it. You do it all the time. And the symbol over here is add them all up and divide by the number of them. Every piece of data contributes. It's because of that, it's influenced by extreme values. Let's say you're looking at heights, and the average, most people are around 5'5" to 6'1", and then you get in a small group of maybe 10 people, there's one person who's 7 feet tall, and this person's a basketball player, volleyball player. Like that one 7 foot tall person is going to pull our mean. It's going to bring that average up pretty high. And so because each piece of data contributes to the math part that add it all up, it means that very, very high scores or very, very low scores end up exerting a lot of influence on the resultant mean. And so means can be really problematic if you have outliers. But there is only one mean. There's only one way mathematically to get to that number. But it could be unrealistic, like 1.5 children per family. Like, what's a 0.5 child? That doesn't make any sense. But we're really we're really familiar with that common term of the mean. Very, very simple. Add it all up, divide by n. It's the sample mean is x bar. It's the mean value group of scores. Sigma means add it all up. X is each individual score, and n is the sample size. So I'm just walking through the math, the technical math part, not super hard. N is the number in the sample. Sample mean is the measure of central tendency that best represents a population mean. If you have interval ratio data, most of the time, the sample mean is the measure of central tendency that best represents the population mean. The mean is very sensitive to extreme scores, so it can skew or distort findings. We'll talk about what skewness is in just a little bit. But skewness is really how different the two measures of the middle can be, the median and the mean. The average means the one measure that best represents a set of scores. There's different types of averages, and the type of average used depends on the question. So instead of just adding them all up together and dividing by the number, you could also do a weighted mean. If you do a weighted mean, essentially what you're doing is you're multiplying a certain number of values in a class group. How many times does something show up? You multiply that value times how many times it showed up, divide all by the total frequency. It's essentially all the same math. Here's an example. It's just a random one. The age at first inauguration. You add up all these ages. Here's how many times it showed up in the data set. So you take the age and multiply it by 2. Take the age and multiply it by 2. And then you total all up and then divide by the number of presidents. So if we look at these really quickly, here's two different ways to look at the mean. The average age at inauguration, this is a histogram of how many people and how many ages they were. The middle right here is 54.584. So this shows up right in the middle of the data. Number of clemencies granted by president, once again, just some random set of numbers. This one's 685. That would be somewhere right in here in this, but that doesn't actually look like the middle. Why does it not look like the middle? Well, there's a couple things that are working here. One president over here granted, somewhere between 3,540 and 4,000 pardons, which has pulled the mean from somewhere in the middle, farther way over here to the right. The other thing is that there were 20-something presidents who granted 0 clemencies. So because there are these extreme scores, the middle doesn't look like it's in the middle. The mathematical mean doesn't look like it's in the middle. Okay, so we've talked about the mean. Another measure of central tendency is the median. This is the middle number. So what we would do is we would take all those values of all the scores and we'd rank order them and then find the one that's right in the middle. Now the thing about the median, a couple things. This is the middle number. It doesn't matter if you have one clemency of 4,000 and 17 clemencies of 0. That 4,000 and the 17, they're all just places in that rank order. So you can have very, very extreme scores, but finding the middle number doesn't involve any math. It's just counting which one is the mathematical middle. So let's say you have 50 pieces of data, right at 25 is the middle. That's pretty cool. Half of the values are above that number and half of the values are below that number. And at most, you might have 2 middle numbers. You just average those 2 together. The coolest thing is the median doesn't look at the value of the number, just its rank. So we talked about this earlier. For interval ratio level data, you can calculate a mean because it has an actual value. But for ordinal level data, which is rank ordered, then if there's a rank order, you can find a median. Same with interval ratio level data. You can rank order all those data pieces and find the middle number. So the median is awesome because you can use it for interval ratio data as well as ordinal level data. Okay, now almost all the time, this measure of central tendency, the median, takes on a realistic value. You're not going to get like 1.5 children, or if you do, it's very, very, very rare. Okay, the median is pretty easy to calculate. It's right in the middle. There's no standard formula, but more or less you rank order the numbers and find the number that's right in the middle. If you're doing something like Excel or using SPSS, you just say, hey, I want to calculate the median, and it gives you that middle number. If there are 2 middle scores, you average them. Okay, now Another really cool thing about measures of central tendency, even though we're talking about the median, which is the middle, you can figure out how much of the data falls above or below a certain point. So the 75th percentile, for example, the median is the 50th percentile, 50% above, 50% below. The 75th percentile means that that score is at or above 75% of all the other scores in the distribution. So let's say you rank order all those scores, you find the middle 50. Well, you could actually look up and try and figure out where is 75% of those scores. Now, the reason you might want to do that is to say, I don't know what the actual score is, but I wonder where I fall in the distribution. In other words, like, where do I rank? And when you ask a question like, where do I rank? You're asking about what the percentile is. So that's kind of a different way to think about where the middle is. If we start looking at medians, this average right here was 54, and the median is actually 55. So the median and the mean are really close at age at first inauguration. If those two are really close, the median and the mean, then the data are not likely to be skewed one way or the other. Now, the median number of clemencies is 419. I think that the previous mean was 685. So 685 is the mean up here. And in this bar is 419. So what's happened is the median, the middle number is 419, but the mathematical average is 685. So in other words, this one way out here is bumping up the value of the numerator, and we're dividing by the same number. So it's pulling, the data are being pulled to higher values. They're being skewed positively. In other words, the mean is positive, bigger than the median is. So it's positively skewed. So positively skewed means the mean is bigger than the median. Negatively skewed would mean that the mean is smaller than the median. And you should think about that a little bit. The way that you get this skewness is as the difference between the mean and the median increases, it looks less and less like it's normally distributed, and then it's skewed. Okay, third way is called the mode. The mode is the number that occurs most often. You make a histogram, look for the peak, or maybe you make a table and look for the value that shows up most often, or maybe you're in Excel and you hit equals mode to find the array and it tells you which one's the one that shows up. The problem with the mode is it doesn't have to be central. It doesn't have to be in the middle. It's just the number that shows up the most. It's very possible that you have multiple modes. You might have a mode, on one end and a mode somewhere else. You can have multiple ones. The other thing is how you build your histogram will throw pieces of data into class groups like 0 to 25, 25 to 50, 50 to 75, 75 to 100. And so how you build your table, how you build your graph will greatly affect how you display the mode. Nevertheless, the mode is a number that shows up very, very routinely. And if you're measuring a classroom full of 20 people and you're looking at their weight, chances are nobody has the exact same weight. So in order to figure out what the data look like, you bump them into clusters and try and figure out, which cluster has the most, which group of people has the most, shows up in the most weight class. So the mode is a way to think about what shows up the most often, but it can also greatly be affected by how you design it. There's no formula. You look for what the mode is the most often. So in this presidential data, there are two modes, 51 and 54. In clemencies, if you actually look at the raw numbers, that 0 shows up the most, or if you build this histogram, it's the class between 0 and 500 that has the biggest lump. They're the modes. Here's a different one, looking at the speed of an accident or how fast people are going when they got a ticket. In this one, the speed of an accident looks like it might be pretty reasonably distributed. How could we figure that out? Well, the median is 35, which is right in the middle. That happens to be the mode. And the mean is 35.6, which is kind of close. All of those three things are right here in the middle. If we look at the velocity of the ticket, how fast people were going when they got stopped, this one person over here got a 120-mile-an-hour ticket. Holy cow. Well, the mode was actually 86. But it doesn't look that way because the 60 to 70 group had a lot of tickets in it. But if we're looking at the raw numbers, 86 actually shows up twice, that exact number. So if we built the categories a little differently, we might get a different mode of categories. Anyway, so the mode was 86. The mean was 78, which is pretty close to right here. And the median was 76. Now, it is up. There is a little bit of skewness here, but you can actually see why that skews, so it's not a huge problem. Okay, so when do you use what? You use the mode if the data are categorical, nominal, or interval. Nominal, ordinal, or interval, you can use the mode. When you want to see which one shows up the most often, mode. You use the median, when you have extreme scores, like you anticipate that there's skewness in the data, or when you have ordinal data. So ordinal or interval ratio data can be used with the median. If you have extreme scores, finding the middle number will help so you don't have to suffer from skewness. Now, when do you use the mean? If you have interval ratio level data that you don't think is skewed, no extreme scores. And so when you have those sorts of things, then you can get the mean, which will be the most precise measure of central tendency, as long as you don't have skewness in your data. Now, we go back to hierarchy of measurement. When can you use what? I put them in here. The nominal level variables, you can only use the mode for. Ordinal level variables, you can use the median and the mode, but not the mean. Only the interval ratio level measurements can you use the mean, median, and the mode to summarize measures of central tendency. All right, so we talked about the measures of central. Now, what's the middle? Now, the next thing is we've got to figure out how else do we describe this data besides saying what's in the middle? Well, we're talking about variance or dispersion. Dispersion is a measure of how spread out the data are. Dispersion really works for interval ratio and ordinal level data because those are the only ones that we can sort of rank, order, or categorize. So dispersion around the mean we call variance or standard deviation, and around the median we call those the interquartile range. So finding the middle, but also how widespread the data are. Let's start with the median. The median is the middle number. So we can describe some of these measures of how the data are spread out a couple of ways. Once we rank order all of the data, we can figure out what the minimum score is, and we can figure out what the maximum score is. That's the difference between the minimum and the maximum score is called the range. Now, exactly in between the minimum and the maximum is the median. The median is the 50th percentile. So 50% of the scores are above the median, 50% of the scores are below the median. That's the exact middle. Now, in between the median and the minimum is the 25th quartile. So in other words, halfway between the first point and the 50th percentile is 25th percentile. And then if you do the same thing between the median and the maximum, you can find the 75th percentile. So 25% of the data fall between here and here, 25% of the data fall between here and here, 25% between here and here, and 25% between here and here. That's super cool. But the coolest part is the difference between this 25th percentile and the 75th percentile. And the numbers, the 25th percentile and the 75th percentile, and the numbers that make that up, that's called the interquartile range. Now, the coolest part about that is that represents the middle 50% of the data. So in other words, half of the data fall between the 25th percentile and the 75th percentile. In other words, between the median, middle, and the 25th and 75th percentile, you've got the middle 50% of the data. And that sort of represents how widespread the data are. So these 5 numbers, the minimum, 20th percentile, median, 75th percentile, and the maximum are called the Tukey 5-number summary, Tukey, Tukey. And he said, hey, look, these are actually really, really good measures of how the data are displayed. Minimum, maximum, middle, and middle 50%. So if you hear me talk about a Tukey 5-number summary, that's what we're talking about. Minimum, 25th percentile, median, 75th percentile, and the maximum. The median tells us the middle number. The range tells us the highest and lowest numbers. The interquartile range tells us the middle 50%. Why should you care? Because that tells you a lot about what the middle of your data are, where the spread is, also from the very maximum minimum, but also the middle 50%. Now, that works for interval ratio and ordinal level data. If you're just having interval ratio level data, we have talked about the mean before. Add up all the data points and divide by the number. Well, how do you measure dispersion around the mean? Like where the data is scattered around the mean? How about you think about it like this? What about, let's try to figure out the average distance a data point is away from the mean. Okay, well, we know how to do an average. Average is add up data points and divide by the number, yeah? Okay, well, the standard deviation follows a similar pattern, except what we're doing is we're adding up, that's the sigma, adding up the difference, the subtract, the data point from the mean. So we're going to measure the difference between the data point and the mean, x1 or xi minus x bar, and we're going to add up those differences. When we add up those differences, then if we were an average, we'd just divide by n. Now here's the problem. If we add up all the differences, we get 0, because that's how the math works. So what we do is instead we square it. That'll add up the squared differences divided by n minus 1. The n minus 1 is a statistical remnant, and it helps us be better at being more confident in our estimate of the variation by kind of overestimating how much variation there is. Don't worry. And then at the end, we square root it. Okay, super easy steps. Calculate the mean, find the difference, square the difference, add up those differences, divide by n minus 1, take the square root. Super easy. So if you were to doing this in Excel, that's what we would do. Speed of the accident, rank order them, subtract by the mean. Here are the differences. Now if you add up all the differences, you get 0. Duh. If you square the differences, then you add them up, you divide by n minus 1, and then you take the square root of it. So the standard deviation is 2.61. Okay, so here you are. The range, slowest to fastest, 31 to 41. Median is 35. 50% of the data fall between 34 miles an hour and 37 miles an hour. That's where the middle 50% of the data are. Then you'd also summarize the mean. The average speed of the accident was 35.6 with a standard deviation of 2.6. Well, what does that mean? Well, on average, the speeds of the accidents were about 2 miles an hour faster or slower than the mean. Okay, so those are sort of like the Tukey 5-number summary, range, median, interquartile range, and then the mean is standard deviation. The standard deviation uses the distance from each of the data points to tell us how different the data are from the mean. So we already talked about why we square those numbers, because they add up to 0. Once again, here's the same example done the exact same way. Now, when you do Excel, you don't actually have to do this. You just have to equal standard deviation, blah, blah, blah. So here we go. The mean is 77.26. The standard deviation is bigger. Why is the standard deviation bigger? Because you have an outlier. That makes the average distance of all the data points bigger. The average distance away from the mean is bigger because you have these outliers that are exerting a whole lot of pressure on that mean to pull it one way or the other. Okay, notes on standard deviation. We almost never use the n for the population. You almost use n minus 1. So why do you do that? Well, you don't really need to know, but it gives us a more conservative estimate of the dispersion. Now, here's the thing that you do need to know. Whenever you're talking about the average of a population, the mean of a population, a mean of a sample, you always always report it with its corresponding measure of dispersion. So if you are reporting a mean, you always write the mean and then the standard deviation together. Well, why? Well, because if the standard deviation is very, very, very large, that's one way to tell that the mean is not a good measure of the middle. Why? Well, imagine that you took a sample of data and the average is 11. And the average, and the standard deviation is 11. So let's say that the mean and the standard deviation are the exact same number. What does that signify? Well, let's interpret it differently. If the average is 11 and the average difference between a data point and the middle, or the mean is 11, that means that almost all your data points are 11 away from the middle, which is 11. So they're like super far away. So if you have a smaller standard deviation, it means that the data are clustered pretty tightly together around that mean. If you have a big standard deviation in proportion to the mean, then the data are scattered pretty widely. And there's no number that says, how close does the standard deviation need to be to a mean. It's just sort of like you get a feel for whether or not it's close to the mean or not. If it's close to the mean, like let's say, once again, 11, and the standard deviation is like 2, on average, the data points are 2 away from the 11. Okay, that doesn't seem too bad. But it's all referenced, it's norm referenced to what the mean actually is. Okay, so we've talked about means, we've talked about, measures of central tendency, we talked about measures of dispersion. How do you otherwise represent data? Well, here's a visual representation of some data. This is by Minard, and it's probably one of the most famous graphical representations of information. It charted temperature and deaths in the War of 1812 as Napoleon's marching to Moscow. Now, most of the time, you're not going to draw something sort of this beautiful. What you're going to draw is you're going to graph information in a way that people can understand it. Because the reason why we draw graphs and figures instead of just reporting information in tables is that they can convey information in a much more clear, concise way, and much more intuitive way. When you illustrate data, you want to measure what the central tendency is, like where's the middle. You also might want to display how widely diverse the scores are. So it allows you to show some measure of variability. There are often different ways, besides just reporting what the mean and the measure of central tendency are, the measure of central tendency plus its corresponding measure of dispersion. If you show me a graph that illustrates that in a really beautiful way, I will understand that much better than having to read those scores in a table. So here's some tips for making a really good graph. Minimize the junk. Make sure it has one central purpose. Not a lot of stuff on the sides. Plan what you want to present before you start creating. Say what you mean and mean what you say. So be very, very clear about any text or any label or any sort of graphic that you put up. Label everything. Make sure that people can understand what you're trying to get at. Communicate one idea. Keep things balanced. In other words, make sure you have the right colors and the sides look symmetrical and there's not a disproportionate amount of information on one side or the other. Now maintain the scale in the graph. So if you have one size thing, you don't change the different scale for a different portion of the graph. Remember that simple is the best. It can look pretty and be simple at the same time. Limit the number of words, and the chart alone should not convey what you want to say. So most of the time with a figure, you're also going to want to write some narrative text underneath it, sort of explaining what your chart says. One of the most simple ways to graph data is to show how often something shows up in the data. A bar graph or a histogram. A histogram is a very specific kind of bar graph that shows a progression along the horizontal axis. The bar graphs are a general category, but histograms are a really specific type of bar graph. So we count how many times something shows up, You have to put things in groups of intervals. You get to choose what those look like. I know that you know how to do all this. But histograms are a specific kind. It's a hand-drawn one. If you look across the bottom, these intervals touch each other. Not all bar graphs do that. The frequency polygon is a smooth type of histogram. Now, for these, this is a pure count. Well, a different way to do that is to cumulative frequency distribution. So between these classes, this adds on to the previous tally and adds on to the previous tally and adds on to the previous tally. Why would you use a cumulative frequency distribution? Well, if you're charting death, where something doesn't just go back down, you're looking at cumulative deaths. If you're looking at cumulative land destroyed or something like that, this might be a better way of talking about it. If you're looking at how fast something gets destroyed, this is also a good thing. All right. Now, when you look at frequency distributions, it's not just that there's a graph there. There's different ways that we can look at distributions to sort of describe them, some vocab terms. So frequency distributions can be different in the average. So all of these have the same shape, but they all have a different center. So this is the average for A, this is the average for B, this is the average for C. So if I were just guessing, you could say the average for A might be 5 with a standard deviation of 2. The average for B might be 8 with a standard deviation of 2. And the average for C might be 12 with a standard deviation of 2. So we describe the middle, but also the range. So these all have different average, but the same standard deviation. This is where they all have the same average, but different standard deviations. So distribution A, distribution B, distribution C, it might all have the exact same average, like 8. But the distribution for A has maybe a standard deviation of 1. The distribution of B might have a standard deviation of 2, and distribution of C might have a standard deviation of 3. So in other words, they can all have the same mean, 8, but how widely spread the data are, the standard deviation or variability, that can affect the shape. So you can see why we would not just talk about, this sample has an average of 8, this sample has an average of 12, this one sample has an average of 6. They all have the same shape, but we're lucky in that they just have different averages. On this one, they have the exact same average, but they have different variation or different variability. That's why we always pair the measure of central tendency with its corresponding measure of dispersion. Now, a different way to think about how data can be distributed would be skewedness. So distribution has 0 skewness. The median and the mean are more or less in the same spot, and the distribution is symmetrical. Skewness in a distribution can also be seen in asymmetry. So distribution A is positively skewed. Why is that? Well, the median is probably here, but we've got some outliers over here. So it's pulling the data this way, the mean this way. It's making the mean bigger than it should be. So it's being positively skewed. Distribution C, the median is somewhere in the middle right here, but the mean is down here lower. Why is it down here lower? Because it's being mathematically pulled lower by a low score. So it's negatively skewed. It's being pulled lower. The mean is being pulled lower. It's less than it should be, so it's negatively skewed. Now, we could talk about platykurtic and leptokurtic and kurtosis, but you don't really need to know any about that. So column charts, bar charts. Let's talk about these. Line charts. Line charts always denote time. Always. So if you're building a chart or a graphic that has a line in it, it's always a trend, and trend almost always is time. Don't build a line chart if there's no time on the X horizon. Okay, so here's a pretty basic, bland, yucky pie chart, but pie charts are really great because they talk about percentages. Pie charts work best if the whole pie counts as 100%. Now, here's all these other ones over here, beautiful ones, and bar charts and line charts, and line charts with different cumulative values. Now look, here on the right-hand side, we have cost per gallon of diesel and fuel charges. If you had to look at this table, or maybe let's say look at this multicolor graphic, which one would you choose? Hands down, you would look at this graphic and try and figure it out before you spent any time looking at this data table. The data table has tons of information in it, but the way it's presented is just not very intuitive for people, and people would just turn their head away from it. So even though we want to do high quality research, we want to show people what's out there. The best way to do that is to bring them in to our project and make them interested. And so we use really good visuals for the data. Another thing is, sometimes our data are really hard to understand if they're just in a table or they're just in an analysis. And this guy, Edward Tufte, this is the cover of one of his books. And this is the amount of O-ring damage at a shuttle launch based on temperature of the joints. So when it's warmer, the damage is on the Y horizon, the Y axis, and damage goes up as you go up the height. Temperature goes up from left to right here. And it looks like the warmer temperatures have very little O-ring damage. But as you move left and get colder, damage goes up pretty significantly. And the reason he showed this one is that a bunch of engineers who were looking at tables weren't really thinking about the potential damage of these O-rings on the shuttle Challenger. Well, when it launched on January 28th, it was exceptionally cold that day. And if you're just having to draw a line to try and map these points, you could predict that there would be pretty significant O-ring damage, maybe all the way up here. And that O-ring damage ended up killing all those astronauts. So, you can look at a table. Ooh, look at all that information. I've got so many information pieces in those cells. But maybe you need to put them in a different way to start thinking about how you use data and what those data trends might look like. Now, mathematically, I can give you some tools for that, and we'll go through that. But graphs are a good way to convey a very simple message very quickly. What I just talked about, too, are correlations. Correlations examine the relationship between variables, how variables change with each other. Correlations generally are bounded by -1 and +1. A -1 correlation would mean that they're perfectly negatively correlated. As one goes up, the other one goes down. And as one goes down, the other one goes up. Okay. Perfect number 1 correlation would mean every time something goes up, the other one goes up. And every time something goes down, the other one goes down. So height and weight are pretty well correlated, not perfectly. As height goes up, weight tends to go up as well. A bivariate correlation is a relationship between two variables, and we'll calculate some of those. The most common of these is called a Pearson product moment correlation, or a Pearson's R. And what it is it's a PRE statistic, an R squared. So a positive correlation is a direction correlation. Variables change in the same direction. A negative correlation is an indirect correlation. So when variables change in opposite ways. Okay. And R x of y is the correlation between x and y variables. So as x is plotted on the horizontal axis, y is always plotted on the vertical axis. This is a data point with an x value of 2 and a y value of 3. Each data point has some characteristic. Like, let's say this is me, and this is number of feet and amount of hair or something like that. So as you go up here, you'd increase the number of feet, and this would be amount of hair, whatever, doesn't really matter. So this is an individual with these two different pieces of information, the x information and the y information. Now, if you were to plot this, it looks like it kind of goes like from the bottom left to the upper right, and we would could draw a line in there to look like a predicted trend. That would be a positive correlation. The absolute value of the correlation indicates strength, but you look for the sign to see if it's positive or negative. So let's just move on to something else. This is how you calculate a Pearson product moment correlation. X is the X variable, Y is the Y variable. All these are different points. Every time you see the sigma, it means add them up. N is the number. The best part about all this is that your statistical program will do it for you, and Excel will do this for you, so you don't have to do it by hand like I did when I was a kid. Not a kid, when I was in grad school. So, you plug all these values into the formula, you calculate, blah, 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 blah. Ultimately, you get this visual picture of a scatter plot, and it draws a line for you. And if this was in Excel, you just click on these data points, and you said add trend line, and it'll give you a linear trend line that'll connect all those data points in such a way that it minimizes the amount of error. So in this upper right-hand corner, this is a strong positive relationship. This is almost perfectly correlated. So something like this would have an R value of 1. This would not have an R value of 1, but it is still positively correlated and is strong. So it's moving in the left to right as you go up direction. This is a strong negative relationship. So as you come over here, as X goes up, Y goes down. That's a negative relationship. And we could plot those, like I said, in Excel. A different way to do that is to look at a correlation matrix like it might spit out of SPSS or some other statistical program. In this instance, income and income are perfectly correlated because they're the same variable. Education and income are positively correlated at 0.5. So I'll show you what some of those pictures look like in just a minute. Attitude, as income goes up, attitude goes down, but it's not a very strong correlation. As income goes up, vote goes down. That's a negative correlation, and it's a little bit stronger than attitude, but it's not as strong as education. So they don't move in the same way. Now, how do you interpret these numbers? Well, upper left, strong positive relationship, strong negative relationship, weak positive relationship. You can kind of see that the data look like this. Moderate negative, really weak negative. How do we draw data points that are connected? Does it go up to the left, down to the right? Nothing. It looks like there's no relationship. So this is what it would look like, kind of. I love this graph, this picture, because it shows you what a super strong correlation looks like down here in the bottom right, negative 0.99. Almost all the data points are lined up in a perfect line. In the upper left-hand side, you have correlation of 0. There's really no pattern there. Your eyes start to play tricks on you, like it might go like this in some way, but mathematically, there's just no correlation if you use the formula. So this one at negative 0.3 starts to bring some of those together. Here's a 0.5, what that might look like. Here's a 0.7. You can see these data points started converging on a line. Here's 0.9. That's pretty tight, but man, look at this 0.99. That's amazing. So there's some real problems with correlation too. Correlation, at least the Pearson's product moment correlation, assumes a linear relationship, like in that upper left-hand corner, that these are all on a line. But we can sometimes generate a correlation. These all have the exact same correlation value of 0.816. In the upper right, we get a same value, 0.816, but it's not linear. We've got a nonlinear relationship that's really perfect. But when we plot it with a linear relationship, we have an equal number of variation on the top and above and below the line. So it maximizes a good line, but it shouldn't be modeled with a linear relationship. It should be sort of curvilinear. On the bottom left, so once again, R of 0.816, but we have an outlier there at maybe X equals 13. Somebody could have entered the data wrong, or really there could be something off the trend line. So if we just get that number and we don't graph the data, we can say, man, this is a really strong relationship, 0.816. But then we graph the data and we're like, oh my gosh, well, I'm going to go check that data point. What happened with this one? Why is this not the way it should be? And you might find out that you've done something wrong. Or it could be that just is the way it is. The bottom right is one of the more intriguing ones. There's really no variation on the X value of 8. And there's one data point out at X value of 19. And that one point at X value 19 is exerting a massive amount of pressure on that trend line. If it had gone down even just a little bit, that trend could be perfectly horizontal, or down in this area and it could have a completely negative relationship. So even though the numeric values of the correlation are strong, this one point could end up making this like negative or positive just by one data point. And really, graphically, if you look at things, you'll see where there might be some errors in your data that you want to fix. So we talked about R, but most of the time we actually square R. And it's called a coefficient of determination, or it's called the coefficient of alienation, or most of the time we just call it R squared. How do you interpret that? Well, if the R is 0.7 and you square it, then you get 0.9. The R squared is pretty awesome in that you can use that 49%, and you can say things like, in this correlation between X and Y, or height and weight, knowing a person's height can explain about 49% of their weight. So once again, if the R was 0.7 and we're talking about relationship between height and weight, we square that value, you get an R squared, and you would interpret it this way. Knowing a person's height can explain about 49% of the variation in their weight. Well, how does that work? Well, if I know what their height is, I can be about 49% sure what kind of weight they're going to be at. Or another way to do that is to say, look at all their height and look at all their weight. You can explain 49% of the variation in the weight based on height. And R squared is what's called a PRE statistic, a proportional reduction in error statistic. We'll talk more about those when we look at a couple other statistics. But the best part about R squared, is that it can be interpreted as a percentage. And so people understand percentages. And so we try and find PRE statistics to summarize our data. So I've written a couple of different ways to look at that here. Including the independent variable in the analysis reduces the error in our prediction by whatever the R squared value is. Or in other words, R squared value of variation in the dependent variable can be explained by the independent variable. There are a bunch of PRE statistics. R squared is probably the one that almost everybody knows, but lambda, gamma, tau B, tau C, Summers D, all these are just PRE statistics, and you can look them up. And you can report the result as a PRE statistic and interpret it pretty easily.